What if we could unlock a new dimension of support for children with autism spectrum disorder, transcending the barriers of conventional therapy? Autism spectrum disorder is a neurodevelopment disorder characterized by deficits in communication and attention, and social robots offer a promising therapy for these problems. Our aim was to implement a gaze classification algorithm to evaluate attention of ASD children and automate manual steps in the context of the early social communication scale. To evaluate the algorithm, we computed accuracy and precision. The experimental setup was composed of 7 targets of attention: the rabbit, elsewhere, now robot, poster right, poster left, poster back, and other person. With a Kinect camera, we recorded different videos under 2 different scenarios, one with the therapist giving instructions to the patient and one with the robot giving the instructions to both. To establish our gold standard for the classification algorithm, we manually labeled the target of the gazes of both the therapist and patient for both scenarios. To improve our gold standard, we implemented a code that compares the labeling done by the 2 people in each video and keeps only the matching lines, classifying all the other frames as no class. Then we built our dataset by integrating these labels with the Kinect motion data. To ensure quality, incomplete data were omitted, resulting in 22 folders for scenarios without a robot and 19 folders for cases with a robot. The experiment videos and the Kinect motion data were then used to generate the gaze angles and the bounding boxes for each frame. Using this output together with the labeling data in the MATLAB code, we implemented the removal of the no-class data to obtain 3 files for each patient and therapist: the indexes of the filtered timeframes, the corresponding filtered labels, and filtered gazes. Then from each video, we extracted the images of the bounding boxes effectively corresponding to the filtered frames, and then we resized them according to the requirements of the neural network. Next, we created 3 codes to concatenate the images, labels, and gaze data to create 3 unique datasets. Using the pickle creation code, the concatenated data were segmented into 3 subsections: training, validation, and testing. From this, we obtained 3 pickles composed of balanced data that will be used to run the neural network. It's important to underline that the low amount of data obtained in this step can affect our final results. Finally, to do the classification, we implemented the training and test code that employs a convolutional neural network for image data and a multi-layer perceptron for gaze data. Using their combination, we trained and validated the network with the corresponding pickles. The results in accuracy, precision, and loss function suggest a possible overfitting that we tried to overcome by changing the number of epochs. Then we gave the test pickle as input to test the model, obtaining the values of accuracy and precision. Our most reliable results are the ones related only to the robot scenarios, consisting of a final test accuracy score of 83% and precision of 41%. To achieve better results along with collecting more reliable data, future modifications such as additional methods to prevent the overfitting and optimization of the parameters of the model can be implemented. Thanks for your attention and Merry Christmas.